Hi, my name is HochangLee. Today, I will introduce an efficient 3D scene exploration method based on view utility prediction. This presentation will contain the following material. First, a brief overview of the chosen paper, followed by the motivation behind the research and some of its related works. Then, I will discuss the methodology and the experimental results. Lastly, I'll finish off by pointing out some of the strengths and weaknesses of the presented method. I chose the paper titled Learn to Score: Efficient 3D Scene Exploration by Predicting View Utility. It was presented at ECCV in 2018. As you can see on the right, the paper proposes an exploration method that can be used to capture and reconstruct 3D areas more efficiently when compared to other traditional methods. An exploration method that uses 3D convolutional neural network to predict the usefulness of future views is presented in this paper. This is a camera-equipped drone that is often used to explore large scenes and reconstruct detailed 3D maps. For this type of robot to efficiently explore unknown areas, it is crucial that the robot can predict how useful the next viewpoints are when it comes to maximizing area coverage. This scoring of viewpoints is performed by the path planner's utility functions. Traditionally, these utility functions were handcrafted by the user, which made them difficult to incorporate prior information about the expected 3D geometry in some cases. Therefore, a 3D CNN model is used to devise a utility function that can predict the usefulness of next viewpoints based on the current occupancy map. Exploration and mapping are widely studied problems. Previous studies include some of the following techniques. Next best view, it is largely concerned with defining a good heuristic utility function and approximating a coverage task. Reinforcement learning with fixed set of camera poses. It utilizes RL to regress a scalar parameter used in the next view selection algorithm. Frontier-based algorithm. It can autonomously map and explore partially known scenes. Most of the research done requires heuristics to decide the next view or prior knowledge about the environment. In this regard, this paper presents a novel approach that is data-driven and can be used to explore unknown areas. A utility function has to predict how much unknown surface can be discovered from a new viewpoint. A well-made utility function would allow the drone to traverse along a path that would provide a maximum coverage of a given area. This would naturally lead to more efficient 3D reconstruction of the area as well. To create this function, the paper proposes a data-driven approach that utilizes values from the oracle as its target. An oracle is a utility function that has access to the ground truth map and can compute the true utility score at each viewpoint. In this example, the oracle could inform the robot that viewpoint B is the next optimal point given the ground truth map containing the true surface voxels. Here are the basics of the oracle. First equation describes the uncertainty that is associated with the fraction of occupied voxel volume when measured from viewpoint P. It indicates that the uncertainty value decreases as the more measurements are taken of the same voxel. The second equation shows that the certainty associated with total number of observed voxels increases as more measurements are taken. Lastly, the third equation is the oracle's utility score expressed in terms of current map M and the camera pose P. High utility score indicates that a lot of information about the voxel surface can be gained when inspected from a particular pose. This ensures that the path traveled by the drone reveals the most amount of information about the area, thus making the exploration more efficient. To train the utility function, a map representation consisting of multi-scale subvolumes are used as the input of the 3CNN. This is done to enable reasoning across larger spatial extents without sacrificing the high resolution gained from small grids. Simply put, this representation allows for capturing the coarse parts of the map that are far from the camera, as well as the finer details in its direct surroundings. The resulting data volume has the same dimension for each scale, and it can be fed into the 4-dimensional array. For all possible viewpoints, this data is fed into the 3D CNN along with the oracle's score as a target value. The network is composed of blocks of 3D convolutions with batch norms and ReLU activation followed by max pooling. When the data volume reaches the size of 4 by 4 by 2, the fully connected layers with ReLU activation are applied along with the final linear layer. Thus, the data-driven model uses Oracle as the reference to train itself, and it can predict the usefulness of the viewpoints based on current occupancy map. The performance of the 3D area exploration based on CNN utility function is compared to the exploration methods based on well-known handcrafted utility functions. Each graph represents the amount of observed surface voxels with respect to exploration time. It is apparent that the suggested method outperforms other handcrafted functions across all known areas. The 3D CNN models holding the closest adherence to the oracle, which is the ground truth. Some people may think that this is to be expected since CNN model was trained with reference to the oracle. Due to the nature of CNN, with enough training, this type of close adherence is very likely to happen. So the real question lies in how the learned model performs when exploring an unknown area. In this experiment, the CNN utility function was trained on the church labeled A, which is located on the top left, and evaluated on the historical building labeled C, located on the bottom left. It is notable that despite the differences in geometry and scale between the two structures, the trained model can generalize to accurately depict a structure that it has not encountered before. Thus, the data-driven method in this case proved to be highly accurate and applicable to unknown areas as well. Here's the video of the explore and 3D reconstruction on various types of areas. As you can see, the algorithm with CNN utility function can explore and reconstruct the area much faster compared to the conventional method, such as proximity count. Here, the trained model is able to explore and reconstruct an area that it has not previously encountered. I will finish off the presentation after pointing out some of the strengths and weaknesses of the proposed exploration method. First, let's go over the strength. The presented method has strong adherence to the ground truth due to its data-driven nature. This method is able to generalize to areas other than training data, meaning that this method allows drones to navigate unknown areas and gather information to reconstruct them. Lastly, the algorithm is efficient in the sense that it covers more area in the same amount of time when compared to other approaches that utilize handcrafted utility function. Some of the weaknesses are utility function is bound to the map resolution and mapping parameters used in the training data. And the area to be inspected has to be a static one. Moving objects can create occupied voxels that do not correspond to the static objects. Lastly, the dependence on surface voxels distribution may be problematic when exploring an area that has vastly different geometries, such as rock formations and other natural things. So that is all for me. I just want to say thank you for listening and make sure you check out the quiz. All right, thank you.